Hello, today's lesson will be a short introduction to solving trigonometric equations. I will show you some of the tips and tricks, or better yet strategies, that are commonly used when solving trigonometric equations. So to begin this, we need to discuss something called the principal values, and these are agreed upon values that we will restrict our angles to when solving because of the fact that by nature, trigonometric functions are cyclic, and thus we have an infinite number of angle solutions we could possibly have. So for sine and tangent functions, we are going to restrict our solution angles to the first and fourth quadrants, so thus between -90 and 90 degrees. For the cosine function, we will restrict our solution angles from 0 to 180 degrees, so the first and second quadrants. This way we don't have to worry about the infinite number of possibilities if we are talking about principal values. The nature of the problem presented may call us to look at other solutions, but this is the default, and if we explicitly say principal values, of course, we will be dealing with these possible solution sets. So let's go ahead and look at our first example. 2 sine squared x plus sine x minus 1 equals 0. This one screams at me that it is a quadratic style problem, thinking all the way back to our algebra courses and solving quadratics. This doesn't become apparently obvious until we look at a little bit of a substitution technique. So if I look at this 2 sine squared x plus sine x minus 1 equals 0 a little differently, if instead I think of this substituting the sine x for another variable, let it be y, so this could be rewritten as 2y squared plus y minus 1 equals 0, it's a little easier to see this as a quadratic. I could then apply the quadratic formula or factoring strategies to solve for y. I'm not going to go over those strategies thoroughly in this video, as that's not the focus of this topic. You can look that up elsewhere on the internet, I'm sure, or ask your instructor. You can ask me if I'm your instructor. But the thought would be, if we use the quadratic formula, that A is 2, B is 1, and then C is -1, and we can go ahead and plug this into a quadratic formula. Remember, for the quadratic formula to work when solving for y or whatever the variable is, we have to have the equation set equal to 0, and then we can go ahead and crank things out, which I've done ahead of time. Okay, so it gives us y is equal to 1/2 or -1 when substituting these in. However, we're not solving for y. We're solving for the sine of x, because that's what we substituted for y. So this actually tells me the sine of x is 1/2, or the sine of x is -1. So where in our principal values does the sine of x equal 1/2? Well, remember, the sine is restricted to the first and fourth quadrants. Sine is only going to be positive between those two, only in the first quadrant. So the sine of what angle is going to give me 1/2 out? So that tells me x is going to be the inverse sine of 1/2, which that is a common trig value of 30 degrees. The other possibility is the sine of x equals -1. Well, that's sine is negative between these two quadrants in the fourth quadrant, and that would be all the way down here at -90 degrees. So I can write x is equal to the inverse sine of -1, so x equals -90 degrees. Now, of course, if these aren't values that we've memorized already, we can use the inverse sine function on your calculator to find these values. So here's our solution. two solutions which we would expect from a second degree polynomial or a quadratic. So that fits with what we would tend to expect. All right, there we go. Let's look at another example. Now this one originally screams to me again to be a quadratic. However, it's not set equal to 0, so I'm going to have to do something here to make that happen. And secondly, notice we are not dealing with principal values. We're looking at all four quadrants, 0 through 2 pi, and the 2 pi tells me we are dealing in radians, not in degrees. So let's keep that in mind for our final answer. Okay? So let's do a little bit of manipulation to our original equation. I'm going to go ahead and subtract cosine squared from both sides so that my equation now reads this. Now the reason why I'm doing this, of course, is so that I am equal to 0, because quadratics generally want to be equal to 0. For many of our solution strategies. But here's the problem now. I've got both sines and cosines. I can't combine those because they're different trig functions to make this fit a regular quadratic problem type. However, if I think back to our identities for trigonometry, there is an identity that will turn cosine into sine. Okay? And so I will rewrite this using that Pythagorean identity that states that the cosine, oops, let me put that minus in there, that cosine squared of x is equal to 1 minus the sine squared of x. We have a Pythagorean identity that states that. And now doing some combination of let's distribute this negative here and make things look a little bit cleaner actually first. Let's do that. Recopy the first part, and now this becomes minus 1, and distributing the negative not only here but to here, this becomes plus sine squared x equals 0. Oh, well, we've got some cool things that happen here now. Minus sine x. Oh, hold on. That's not the one that cancels here. I need to be careful. That does not cancel. All right. Oh, I've got a little excited there, and I shouldn't have made that mistake. That does not cancel. However, I do have something else that cancels. I was getting excited that more would cancel, but those two definitely cancel out. Plus 1, minus 1. However, I can go ahead and combine my squares. So that tidies things up still a little bit, giving me 2 sine squared x, then minus the sine x that's still there, equals 0. All right, so what strategy do I want to use here? I could put a c term of plus 0 here and apply the quadratic formula. However, I think that's creating more work than what we need to do. Let's factor out a common factor of sine x here. Sine x. And when I factor that out of the first term, that leaves me with a 2 sine x. Factor it out of the second term, that leaves me with a minus 1 equals 0. And now I can apply my zero product property that says if I'm multiplying two things and their product comes out to 0, one of those two things must be 0, one or both of them. So that tells me either sine x is equal to 0 or 2 sine x minus 1 equals 0, or both. So if this first one's the case, where between 0 and 2 pi does sine equal 0? Well, that's going to happen at pi radians. So x equals pi. It would happen again, actually, at 2 pi, but notice the restriction on the domain says that we cannot be equal to 2 pi. So we're just stuck with just pi there. Over here, if I do a little tweaking of this, I get sine x equals 1/2 when I solve that. So where is it equal to 1/2? Well, sine is going to be positive in quadrants 1 and 2. So that tells me x will equal 30 degrees, which is pi over 6. and also at 150 degrees, which will be 5 pi over 6. There we go. So my solutions would be x equals pi, and x equals pi over 6, and 5 pi over 6. Those would be my possible solutions for this. And a good practice is to plug them back in and make sure they work. Interest of time, to keep the video short, I'm not going to do that. But that would be your next step. All right, so let's take another look at a problem. This one we're going to be looking for all real values of x. And boy, this looks like a beast of a problem. I'm not restricting x, so let's see, what kind of strategies could we use? It doesn't look like a quadratic, and not seeing things that can be combined here to simplify. However, I do notice there are 1, 2, 3, 4 terms, and classic math textbook problems say when there are 4 terms, to try the strategy factor by grouping. Now, factor by grouping works by cutting the terms in half and looking for a common factor in the first 2 terms and a common factor in the second 2 terms. If your book is really being challenging, they may have you reorder the terms, but most math textbooks aren't going to do that to you. So the common factor in these first 2 terms would be, I could factor a 2 out from both of these and a sine out from both of these, leaving me with then 2 sine x being factored out. This term, when I factor out 2 sine x, leaves me with another 2 from the 4. Dividing out 2 gives me 2. And the cosine function is still there. And the second one, I'm going to factor out the 2 sine x, just leaves me with 1. Okay, so minus 1. Now, to get a matching 2 cosine x minus 1 over here, I would actually factor out a negative square root of 3. So I'm going to pull out a negative square root of 3. And when I divide that out of my first term, that leaves me with I took out the negative, took out the square root of 3, so I'm left with 2 cosine x there. And I factor out negative root 3 here, that leaves me with a negative 1 on that one. Now I'm going to factor again a common factor from both this term and from this term. And that common factor will be my 2 cosine x minus 1. It shows up in both places, so I'm going to pull that out from both of those out in front. 2 cosine x minus 1. And then what I'm left with, in the first term, I'm left with a 2 sine x. And in my second term, I'm left with a minus root 3. Fantastic. Equals 0. Now again, using the zero product property, either this term must equal 0 or this term must equal 0. So let's solve each of those. 2 cosine x minus 1 equals 0, or 2 sine x minus square root of 3 equals 0. Do a little algebraic manipulation here. I get cosine x equals 1/2. Now, where on the unit circle does that happen? That will happen at, well, let's go with degrees. A lot of people are really comfortable with degrees, and I didn't specify here. So that cosine x is going to equal positive 1/2 in the first and fourth quadrants at x being 60 degrees, and also at x being 300 degrees. Now I want all real values of x, so I have to consider every time we go around the unit circle, those values are going to happen again. So I'm going to put on multiples, and I'll use the variable k for integer multiples of 360 degrees. And I'll do the same for 300, so integer multiples of 360 degrees. That accounts for I'll give you the example with 60 degrees. We have 60 degrees, but then I'll get that same x value happening when I go around the circle again. There's one multiple of 360, and again, another multiple of 360. I have to put every time I go around the circle. Another way to look at that is on the cosine graph. This keeps repeating like this. Where is it going to come out to 1/2? Well, it happens here, at 60, and then at 300. And then if I travel another 360 degrees down the circle, it happens again. And it's going to happen every 360 degrees down the graph of this function. Okay, so that's what the K360 does. It counts for all the multiples of 360 down the road. Just remember, we have to tack this on whenever you see all real values. Okay? Now let's finish this other one up here quickly. So do a little algebraic manipulation. We get sine x is equal to the square root of 3 over 2. And that is going to happen in the sine is going to be positive in the first and second quadrants. So that would happen when, let's see, x is going to be 60 degrees again for the first quadrant, but then in the second quadrant, we get that at 120 degrees. And then, of course, we have to put in that K360 on there again. K360. So altogether, my solutions, I have two solutions here, but one of them is actually repeated, so let's not count that. I have another one here. So there's a third possible solution. You could even tidy this up possibly a little bit more. No, you couldn't. Never mind. So there we go. There are our solutions for this one. We have 3 possibilities. Pretty cool. 4 really, but this one is a repeated solution. Okay. All right. That was. Okay. Sorry about that. The bell rang. Let's finish the last problem here. This is an inequality, so things are going to be a little bit different. However, just like when you're solving regular equations, this doesn't change things very much unless you divide by a negative or multiply by negative in the solution process. Again, notice that the angle is not restricted to the principal values. We have one full revolution around the unit circle. Let's go ahead and solve it. So I'll begin by taking my inequality, and we will try to isolate the trigonometric function. So let's subtract 1. 2 sine theta then is less than -1. Divide both sides by 2. And we have sine theta is less than -1/2. All right, so less than -1/2. It may be really useful to look at what this looks like on the unit circle. Okay, so I'm going to go ahead and sketch that out. Now remember, sorry for the horrible circle there, remember sine values go with our y-axis, our vertical axis. So -1/2 is about right here, because remember the very bottom is -1. So less than -1/2, we're talking about the portion down here. Really, this part of the unit circle is where the y values and thus the sine will be less than -1/2. So where is that? Well, to hit -1/2, that is going to happen where? Well, this would be pi over 6 past pi, so that would be at 5 pi over 6, and pi over 6 before 2 pi, so that would be 11 pi over 6. So we're saying theta is between 5 pi over 6 and 11 pi over 6. That will give us y values less than -1/2 and thus sine values less than -1/2. Okay? So theta then will be greater than 5 pi over 6 and less than 11 pi over 6. And I don't say greater than or equal to or less than or equal to because this is strictly less than. Okay? So when we can see that on our diagram here, it has to be greater than 5 pi over 6, but then I have to stop before I get to 11 pi over 6. And that would be my solution set. So with inequalities, I think it really helps to draw out the unit circle. Okay? All right, for my FST students, here is the book assignment. For the rest of you, I hope this is helpful in some way. Good luck, and go have some